in this family of infinity, I have just one vector field. If I do the bracket with itself, I get 0. So this is indeed the same thing, which is not R3. Now, this R3 is different from that R3, right? This should be your all your admissible velocities if you have an anthropometric constraint set. If you don't, this is the tangent bundle. This is the tangent space at Q naught. If you don't have constraints, they will be the same dimension. So the system is not even configuration accessible. And if it's not configuration accessible, it's not small time locally configuration control. Using just this guy, which makes sense. I mean, if you gotta just do this, you will never rotate the thing if you start stationary, right? If I start stationary. Let's see the other vector. So using the torque only, so I have y2 was 0, I guess this 1 over I, 1 over ml squared, and negative 1 over I. Okay, I'm going to do symmetric product, so y2 with itself, and if you do it with itself, so this is twice the covariant derivative y2 in its direction. Let's do that here. So I'm going to copy this, and I have y2, 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 and f5. So this is the vector. Let's do simplify. So yeah, it's negative 2 m squared L cubed. Very good. So this is negative 2 m squared L cubed down 0, 0. That's interesting because this is a new direction that you can generate force. This guy was not generating anything in the radial. Now I can generate in the radial by doing the torque. I can generate in the radial. How's that? Any idea? How do you generate an acceleration in the radial with just moving?
Curious.
That's centripetal, right? So, or let's see, the thing that you don't like.
Yeah.
Okay, so we got this centripetal action. We can generate an acceleration. Okay, that's very good. Let's keep doing symmetric products, right? Let's do symmetric product now of y2 with this guy. Iterated symmetric product, right? So let's do symmetric product of y2 with this guy. So I'll take this. So now it's not with itself, it's with different vectors, so there's no the factor of 2. So I need to compute the covariant derivative of y2 along y2 and the other way around. This is plus this guy. Here is the other way around. So this is y2, y2. I guess that's okay. Let's compute this. Without substitution, it's 0. Okay. So we can have okay, this guy with itself. So this is y2, 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 y2. This guy M4, L7, and 24. So this is first was 0. And the symmetric product of this guy with itself was something like negative 24, L7, M4, I guess. But this is not a new direction, it's actually in the same direction. And if you keep doing this, you will not get anything beyond just the first component. So it's nothing new. So the sim infinity, the accelerations that you can generate is the span of y2, which covers one dimension in the tangent bundle, and this guy. Okay, and this covers just R2 at most, which is less than R3. So what's the conclusion? it's not accessible. And if it's not accessible, it's not small time locally controllable. Let's hope for the configuration kind of thing. Let's hope for the configuration. So the configuration, you just do lead brackets between these guys, right? That's it. Okay, so actually I need to do y2 lead brackets with the symmetric products y2 and y2. So let's do that. So these are just zeros, I don't need anything. Here I'll do lead bracket, this is again another thing. You give it q, and you give it the two vectors, y2 and y2, y2. So, we got this vector, m cubed Ls in the second direction. So this is 0, -4, m cubed Ls and 0. So actually this guy with y, with the symmetric product covers the first direction, right? This guy covers the first direction. y2 itself, so this covers the first direction, this covers the second, and now y2 can cover the third. So actually the three together, they cover the tangent space. So the Lie infinity, I don't need to do anything more. So Lie infinity of sim infinity of y is just the span of y2, which now covers the third direction. This guy covers the first direction, and the Lie bracket y2 with. Look at how one control acceleration can do many things. Look, we're just repeating y2 in different scenarios, right? This is indeed R3, which is the tangent space of Q for any Q. What do you get here? What is the result? It's configuration accessible. Is it small time locally configuration control? Well, the theorems that we have are just for accessibility always, and you just check that by seeing if you are relying on a bad bracket or not. If you're relying on a bad bracket, it's not the end of the world. You need to see what is a weaker sufficient condition to use. But let's see first, are we relying on a bad bracket? Yes, this guy, remember this, what is this guy in your space? This was y2 lifted, s, which is the drift, y2 lifted. So this is a bad bracket. That's okay, we need to go and see if we can neutralize it or something. Use one of these theorems that we did not have in class, just one that we did not have in class, Sysman. But remember I told you once that if you have just single input, if I have a single input system, this particular Lie bracket, if it doesn't vanish or if it's providing a new direction, if you rely on this Lie bracket, your system is not small time locally controllable. And this is actually Sysman 1983. So yeah, a single input here, we're doing the torque only, and I'm relying on this guy, so my system is not small time locally configuration controllable. So this is on a side. Not. Okay, any question about that? And yes, think about it, because yes, it provides me a radial acceleration, that's fine. So when you just do this, you'll go out. And if you do the other way, you'll also go out. You don't have an ability to move inward. So this is, by definition, it's really accessibility, it's not controllability, right? But for the configuration space. Any question about that? Let's do both and see what we get. So 3, we'll do it using both. So we have y1, or our family is just y1, 1 over m0 and 0, and y2 is -1 over I and something here, whatever. So that's okay, I'm going to do symmetric products. I already did symmetric product y1 with itself before and it was 0, and I did symmetric product y2 with itself before and it was, anybody remember, it was something like a negative 2m squared L cube, I guess. 0, 0. If you look here, let me just do it clearly. This is m squared L cube. If you look here, this guy doesn't provide a new direction. Before, when I considered y2 only, it was new with respect to this guy. But with respect to the family, this is not a new direction, right? This is actually negative 2 divided by ml cube times y1. It's not just that factor times y1, but this is a C-infinity function because L is a value. It's not a new direction, which is good and bad, right? You're hoping for new directions, but not bad new directions, because this was bad, right? Although, in this case, this is indeed a bad bracket, but it may not rule out controllability, because it's not single input. That condition, the blue condition here, was for single input. If you rely on this guy for single input, for sure you're not controllable, but for multiple input, you don't know, okay? But anyway, it's not new in any case. So let's do symmetric product y1 with y2. I guess this is also 0. And you keep doing it. I mean, we did this before. With y2 gives you 0. With y2 and y2 it gives you not a new direction, the first direction, not new. We did this before. So actually having them together didn't help much in terms of accessibility. So the sim infinity of the family didn't change. It still spanned the same thing. It's different vectors. It's just y1 and y2. But it's the same thing. It's R2 at most, which is not R3, so the system is not accessible even with two controls. Not accessible. And it's not small time locally controllable in the entire state space, position, and velocities. Yeah, indeed. This is why under actuated system, I have 3 degrees of freedom and 2 controls. This is an under actuated system. Dealing with under-actuated system is hard, because how can you generate acceleration or force in the other missing direction? You will not be able to do it all the time. This is indeed hard. So this is why we have the relaxed notion of configuration accessibility and small-time local configuration control. Let's focus on the positions. It's hard to achieve velocities in a very, very short time, which means hard to achieve accelerations. It's hard to achieve accelerations. But we can achieve velocities. So let's do Lie infinity of this family. So let's do the y1 with y2. Simply. Remember, if you want to do these computations with a very generic thing, all the computations will be done on the 6th dimension. Okay? Here, breaking it down like this, we're doing all the computation in the 3 dimension. It's much less computation. So if we were to do it in the generic sense, we would do, yes, indeed, y1 and y2, but in the lifted space, okay? Not here in the 3 dimension. So let's do Lie bracket y1 and y2. So this is like so we get again negative 2 m squared L3. So this is 0, negative 2, m squared, L3, 0. So you can see that this guy, along with that guy and that guy, the 3 give you the entire tangent space. So indeed, the Lie infinity of sim infinity of the family y is the span of y1, y2, and their Lie bracket. This covers the entire tangent space for all Q naught. So what do you get? What do you conclude here? The system is what? Yeah, configuration accessible, right? This is configuration accessible, which indeed expected, because when we did it with just kinematics, respecting the outcome of the dynamics, which is the conservation of momentum, we got that we are accessible in the configuration space only. So here we're covering it with dynamics as well. Is it small time? locally configuration controllable. Is the small time locally configuration controllable? Are you relying on bad brackets when ensuring accessibility? We're not relying on any bad brackets, right? This is y1, y2, and y1 and y2. So this is indeed yes.
Professor, but the bad bracket doesn't match, right? It doesn't match. I'm not relying on it, but it doesn't match.
It's in the space of it can be spanned by lower brackets. So the necessary condition, if you wanted the exact form, if this guy is not in the previous things, lower order Lie bracket, like first order Lie brackets, is not in the span of brackets with 1G, this is the exact state. Okay?
Professor, I have a question.
Sure.
From a physical point of view, you said that it's hard to get accelerations, but I say it's impossible.
Force here.
What?
Now we're doing it with both. Remember, this is with both. So I have the force to get back and forth, and I have this guy.
Yes.
And I couldn't get accessibility, which means what? I don't have the ability to generate acceleration in the theta of the body. So I can let the body move to the angle that you like. That's fine.
Yes, depending
But
on...
I cannot generate a move. If the body, say somebody is moving me and I want to resist, I will not be able to do that. I can't balance.
Yes, but how did we get this? Due to Coriolis forces.
Get what?
That acceleration of the body.
I said I cannot get it. It's not accessible. So using both, let's see, using both. I have these two vector fields, okay? One covers the radial, and this guy covers them combined, so it's not them independently, right? Okay, so you can generate one acceleration but not the third. And keep doing symmetric products, I didn't get any more. So I cannot generate three independent accelerations, I cannot. Just two.
Yes, okay.
For the forces, I have two forces already. I have
Yes.
a force and I have a torque. So
Yes.
of course I can generate two.
That's what I'm asking. So it will always be that case.
No.
Because why?
No. Because sometimes the drift gives you the ability, the interaction between your forcing and the system dynamics sometimes give you action in flapping. So in flapping flight, for example, when you do, it has to abide by the physics at the end of the day. In
Yes.
flapping flight, when you do like this back and forth, right, this is indeed a symmetric product. The result is the symmetric product of the control torque. You have a control torque input for this guy affecting the state space of that guy and state space of the body. The interaction of this motion with the drift of the body. What's the drift of the body coming from? From aerodynamic forces.